Hello there, my name is Connor Mead with the Calculation Center, and I'm just doing a short video here on the determinant of a matrix in our linear algebra series. Now, the determinant of a matrix is a quantity that we often want to compute, but often the computations of it are often hidden behind difficult notation and confusing ideas. So this one will be focusing on the actual computation of the determinant, how to figure it out given a matrix, and what are some tricks we can learn to compute it easily. So basically, if we're given a matrix A with the components Aij, and A is an n by n matrix, so A is a square matrix with n components, n rows and n columns, then we can define the determinant of A. Now this is probably, if you're given a definition of the determinant, this is probably what you see, is that the determinant of A is the sum over sigma, being a permutation in the permutation group Sn, of the sine of sigma times each of the components of AI times the corresponding permutation of I. If this seems a bit scary, don't worry, we won't be working with this. This is like the technical definition, but isn't really the easiest way to go about computing it. And just as a side note here, we sometimes denote the determinant of A, which we write as DETA, is sometimes noted as just this kind of A with two bars around each side of it. Okay? So why do we care about the determinant? Well, these are the three reasons that came to me immediately. There's obviously going to be a lot more if you're more involved in maths. But if you're, generally speaking, if you're just doing a linear algebra course, the main three times you're going to compute your determinant is to check if a matrix is invertible, because the determinant of A is equal to 0 if and only if A is not invertible. Okay, so that means if A is not invertible, the determinant of A is some non-zero number, and if A is invertible, then the determinant of A is just 0. Okay, so if we compute the determinant of A, we can see whether or not A is not invertible. Okay. Secondly, for a similar reason as the first one, the determinant of A is equal to 0 if and only if the columns of A are linearly independent. Now, we won't be going into much about linear independence in this video, obviously, but just know that if you want to check if you've got a collection of vectors and you want to see if they're linearly independent, there's lots of different ways of doing this. One way you can do this is by putting each of those vectors as a column and making up a matrix by this, and then computing its determinant. And if that determinant comes out to be 0, then those column vectors are going to be linearly independent. And lastly, the third one is it lets us compute the characteristic polynomial of a matrix A. Okay, so we can define this thing CA of lambda, and it's equal to the determinant of A minus lambda times the identity. So obviously it depends on lambda on this right-hand side. But the important thing is it's the characteristic polynomial of A and has its eigenvalues as its roots. Now, if you haven't done eigenvalues in your course yet, or if your course isn't covered, you can ignore this one, obviously. But just know this is another reason why you might need to compute the determinant of a matrix, and our methods will work for that. Okay. So let's get on to the actual computation. I've got three matrices here. A, B, and C, each of different sizes. So the determinant of A, so A is obviously a 1 by 1 matrix, B is a 2 by 2, and C is a 3 by 3. And let's say we want to compute the determinants of each of these ones. And I'm going to kind of do this dogmatically in some way, since I'm going to tell you how to compute these. And I'm going to not explain myself any further. The determinant of a 1 by 1 matrix, we're just going to learn off what this is, okay? The determinant of a 1 by 1 matrix is just equal to the number. Okay, so we say determinant of A is equal to the determinant of the matrix 3, or the matrix which only has one entry, which is 3, and this is equal to 3. Okay. This is going to be this is perhaps obvious to people who've done a little bit of this work, but this is just to build the framework of how we're going to go about this, because generally the best way to compute a determinant is to compute a bunch of smaller determinants. Okay, so what we're going to do here is I'm going to kind of describe a game we play to compute these determinants. Okay, so we choose the top left-hand entry here. So we're going on to compute determinant of B here. We're going to choose this top left-hand entry here and write it down. And now what we're going to imagine doing is we're going to imagine crossing off these two lines here. We're going to remove all rows and columns containing the number we just wrote down. So we wrote down this 2. So we're going to cross out the row with the 2 in it, and we're going to cross out the column with the 2 in it. Just this instance of 2, of course. Okay? Now, we're going to look at what we have left. We have just left this minus 3. Okay? So this minus 3 is like a sub-matrix of our big matrix, right? So we've got a 2 by 2 matrix here, and this is just a 1 by 1 matrix down here. So what we're going to do is we're going to write down our sub-matrix here and take its determinant. Okay? 2 times the determinant of minus 3. And then what we're going to do is we're going to, so basically there's an implicit plus here, and we're going to also write down this plus again, except we're going to switch its sign every time we go around. Okay? So by that I mean, basically I'm going to write down a minus sign here, because I have a plus out in front. Now, what we're going to do is we're going to write down, so we've written down this 2, now we're going to go 1 to the right and write down this 1. Okay, so we're going across the top column, to the top row here. So what we do is we now do the exact same thing we did before. We cross out all the rows which contain the 1. This contains a 1, so we cross it out. This is a minus 3 here, so we cross it out. This column has the 1 in it, so we cross it out. And we're only left with this submatrix 1 down here. And we're going to again write down the determinant of 1. And what do we get here? Well, we know how to compute the determinants of 1 by 1 matrix, I told you how to do it up here. So this determinant of minus 3 is just minus 3, and this determinant of 1 is just 1. So what do we get? We get 2 times minus 3, minus 1 times 1. And this is obviously equal to minus 6 minus 1, so minus 7 in total. Okay? Now, just as a little bit of a side note for this one, because this is going to be a useful trick if you have to compute determinants in your course, is that if B is equal to A, B, C, D, so these are just four numbers, then the determinant of B, we can just write it down. I went through this kind of process because it's going to be useful by 3 by 3 matrix, but here the important thing to note is the determinant of B is actually always going to be AD minus BC, okay? If we just follow these rules here, okay? So it's the first times the fourth minus the second times the third. It's just useful to have the idea of how to do a 2 by 2 matrix quickly in your head when it comes to the 3 by 3 matrix, which is generally, most of the time, if you're asked to compute a determinant in a course, it'll be a 3 by 3 matrix. So, like I said, I kind of went through this a bit slowly. I could have just jumped straight to this end here and given you the formula, but it's useful to have gone through this process here to understand what we're doing here. Because the formula, like you can write out a corresponding formula for 3 by 3 matrices, like you can up here. But it gets a lot messier for 3 by 3 matrices, so it's better to know the method in this case as opposed to the formula. Okay? So what do we do? Let's remember what we did last time. We wrote down a plus out in front. We picked the top left-hand entry, and we wrote it down. Then we crossed out all matrices, or all columns and rows that contained our 1. To be clear, I'm not talking about the 1 over here. Like, I'm not crossing out this column. I'm only crossing out the column and row that our first entry appears in. Okay, so just this first row and first column. Okay, and we multiply it by the determinant of the remaining submatrix. So we're left with this little matrix here. So we're multiplying 1 times the determinant of 0, minus 4, 1, minus 1. Okay? And then we have to go on and play the rest of the game, which I'll do in just a second once I've tidied this up. Okay? So that should be 4. Now, so that's our first one. So we remember, now, this is like the first part of the game, right? We do this basically once for each column or row in our matrix. So here we've done it once, so we'll have to do it again, and then again, because we have 3 columns. So we write down, this was plus, we flip the sign, we get a minus, because remember, every time we go on to the next part, we flip the sign. We write down, we go 1 to the right from this 1, onto this 2, circle it, and write down the 2, and then we cross out all columns and rows. Now this is a little bit weirder, because we don't have a submatrix, but we just imagine sticking these 2 bits together, this 4, 2, and this 0, minus 4, minus 1. So we just write down the determinant of 4, 2, minus 4, 1. And remember, since we know how to compute 2 by 2 matrices, the determinant of 2 by 2 matrices, this should be quite easy for us to compute. We can just use this formula up here. Okay? And lastly, so that's the last bit of, that's part 2, I should say. Let's get rid of all this. So that was a 0, I believe. And lastly, so we have a minus sign here. We flip the minus to a plus. So notice the pattern here. We go plus, minus, plus. Okay? Write down the 1 here. And I also want to make clear, if this was a negative number here, this plus, minus, plus pattern wouldn't change. We just multiply the first term by a negative number instead of a positive one. And then we just write down the determinant of, we cross out everything containing our last entry, 1, 2, 1, just this. And we're left with just the determinant of 4021. Okay? And now at this point, it's just a case of computing this. And like I say, we could go through this again. We could work out these determinants individually. It's the first, we write down the first one, take the determinant of the remaining submatrix, and so on. But it's actually going to be easier for us here to just apply this formula up here. Okay, so this is equal to 1, and then we take the first, multiply by the fourth, so 1 times 0 times minus 1, minus 4 times 1, then we minus 2 times 4 times 1 minus 4 times 2. And lastly, we add on plus 1 times, the term to this is 4 times 1 minus 0 times 2. Okay? The first times the fourth minus the second times the third. Okay? And now it's just computation. So this is 1 times minus, the minuses cancel here, so we actually get 4. So minus 1 times minus 4 is a 4. Here we get minus 2 times 4 minus 4, so this is actually plus 8, so it's 12. So it's minus 2 times 12. And this one comes out to be plus 4. Okay? And does this all work out? This whole thing comes out to be 4 minus 24 plus 4, so it's 16. Okay?